Hello, welcome to section 3, part 2 of chapter 5. So we're still working with differential equations, but this time I'm just adding on, instead of just finding the general solution, we're going to find a particular solution. So remember in the first section we said a particular solution is they have to give you initial conditions. So they're going to tell you like y equals this when x equals this. So all we're doing is at the end, after we get our general solution, we're going to plug in our initial conditions, and then our final answer won't have that plus c part because we're solving for c at the end. So in general, your steps are going to be find the general solution like we've done. So we've been doing separate the variables and then integrate on both sides with the y's and then integrate with the x's. And then one change is that you don't have to find or get y by itself at the end because we're going to plug stuff back in. So step 2, plug in the initial conditions that they're going to give you, and then that should be it. So let's do a few examples. So in this example, we're going to be given the initial condition of y of 0 equals 1. So remember, this just means that x equals 0, y equals 1. So that's what we're going to be plugging in at the end. But here's our differential equation. We've got the x's and y's mixed in there. The dx dy is already split up for us. So remember, our goal is to get the y's on one side, x's on the other, and then integrate from there. So my first step is I'm just going to subtract this xy dx on both sides. The reason I'm doing that is I know the dx I want to end up on the right because that's what I'm used to, but you could have moved this stuff over to the other side as well. Doesn't matter. But again, we're trying to get x's and y's on one side or on a single side. So I'm going to choose this side to be the y. So I got the y's over here, which means I need to divide this out onto the other side. And I need to divide the y out from this side over here. So I'm going to end up with y squared minus 1, and then I'm going to divide it by the y, dy. And then on the other side, I have the negative x on top divided by this e to the negative x squared dx. So now my y's are on the left and my x's are on the right. So this is the part where we want to integrate both sides now that our variables are separated. So looking at the left side, we've got fractions, which is not good. I'm going to try to simplify this since I only have one term on the bottom. So let's divide both terms on top by y. So I can turn this into y squared over y is just y minus 1 over y dy. Okay, so that looks a lot easier to integrate. And then on this side, I don't think I can do anything like that type of dividing, but it does look like I'm doing e to the negative x squared. So maybe let's do u substitution. So I'll say, so I've rewritten this side. Since I have a negative exponent, I can change that into not a fraction anymore, so that I end up with a positive exponent. And then I set, because I have e to the x squared, that's kind of complicated, so I'm going to set u equal to x squared. So that would make du equals to 2x dx, and then I can use u sub to rewrite this entire equation in terms of u. So because my du equals 2x dx, I have a negative x dx already. So if I multiply it by another negative 2, that'll make it a positive 2x dx. So I can substitute all of that stuff with du. And then my e to the x squared would turn into e to the u. Because I multiplied by a negative, though, I would also have to do the opposite and multiply it by a negative 1/2 on the outside. So integrating that, I end up with negative 1/2 e to the u, since the integral of e to the u is just e to the u, and then I plug the u back in. So that's the right side. I'm done on that side, so let's integrate my left side this time. So integral of y is just y squared over 2 minus 1 over y would just make it natural log of y. Oh, let me rewrite that down there. And then I'm not putting the plus c because I would have ended up subtracting it over to the other side anyways. So there we go. So I have integrated both sides. I don't have dy dx's anymore. So at this point, Normally we would go about and try to get y by itself, which in this case looks kind of crazy anyways. So we don't need to do that anymore. At this point, now that we've integrated on both sides, we just need to plug in our initial conditions. So anywhere I see x's, I'm going to plug in 0. Anywhere I see y's, I'm going to plug in 1. And remember, the goal is to solve for c. Okay, so plugging in 1 for y and 0 for x's, I'm going to simplify. 1 squared over 2 becomes 1/2. Natural log of 1 is just 0. E to the 0th power is just 1, so multiplied by negative 1/2 would be negative 1/2. I can add that over to the other side to end up with c equals 1. Okay, so then my particular solution, I'm just going to plug that back in for c and then kind of like simplify things a little bit. So originally my general solution was here, because that's when I finished integrating everything. So my particular solution is still going to have the x's and y's in there. I just have plus 1 instead of the plus c. And then just to make things a little bit nicer looking, I notice I have fractions here. I don't need them. If I multiply everything by 2, it'll just make things look nicer. Because then I'll end up with y squared minus 2 natural log y equals negative e to the x squared plus 2. And then I can make it look real nice, because if I have a number in front, this is the same as putting an exponent next to the y, which anything squared is always going to be positive, so I don't even need the absolute value signs anymore. And if I add the e to the x squared over to the other side, now this looks so nice. Look at that, all of that equals 2. And that part isn't quite as necessary, it just looks nice. Okay, let's do another example. So this time I've got 3x squared y prime minus x equals 0. And they've given us the initial condition that y of 1 equals 2. So first I'm going to separate my variables and rewrite my y prime as dy dx. Okay, so as you can see, I added x to both sides, and then I divided both sides by 3x squared, and then I also multiplied the dx over to the other side. X over 3x squared simplified to 1 over 3x, and then on this side I'm just left with y squared. So from here we can integrate since my variables are separated. On this side, the integral of y squared is just y cubed over 3. On this side, 1 over 3x. I'm going to rewrite this as 1/3 times 1 over x first, because it's a constant. So this is really 1/3 times the natural log of x plus c. Okay, so I've integrated both sides, so this is my general solution. So at this point, we're going to plug in x equals 1, y equals 2. After plugging everything in, I got c equals 8 over 3, so we can plug that in back into our general solution again. And then, again, just trying to make it look nicer, I've got fractions on everything, so let's multiply everything by 3, and that'll get rid of any fractions. And there's my particular solution. All right, for the last example, this time, rather than giving us a differential equation, I'm going to give you the equation of the slope. So it says that slope is negative 4x over y cubed, and we're trying to find the equation of the curve that passes through this point, 3, 2. So this is kind of like our initial condition, because they gave us an x, they gave us an y. And if they gave us a slope, that basically means, remember, slope is just another word for derivative. So if the derivative is negative 4x over 3 over y cubed, then dy dx equals negative 4x over y cubed. So at this point, let's find our general solution. So I separated my variables, And then I integrated both sides to get y to the 4th over 4 equals negative 2x squared plus c. Plug in my initial condition to get c equals 22. So from here, plugging back into my general solution, and again, I just don't want fractions, so I'm going to multiply everything by 4. And there we go. That's the equation of the curve that passes through the point 3, 2 and has a slope of negative